All right, let's talk about the shell method. Section 8.3 continues here. The shell method is another way to find a solid that's generated by revolving a region around an axis of revolution. And it shows up in a situation where, let's suppose, kind of like the warm-up problem we did prior to this lesson, where there's an area that you're revolving around an axis, and it is in terms of x or y and can't be changed into the other form. So, for instance, if I had x squared, y equals x squared minus x plus 7, and I wanted that to be written in terms of y. In other words, I wanted to get x by itself. That would be impossible to do. So if it was a region where I needed it in terms of y, but in order to use the disk or the washer method, but I can't turn it in terms of y, or get it in terms of y, then I would need to use the shell method, okay? So we'll deal with some examples here in a second, but let's just set this up in general first of all, okay? So in this situation, or I should say this, the shell method will be used in situations when the rectangle, the cross-section, is parallel to the axis of revolution, okay? So here's our axis of revolution. If it's parallel to it, then that's when we will end up with using the shell method, okay? And we're going to set this up. I'll sketch this in a second for why this is called the shell method, but we're going to set this up. We're going to call that distance h. That's going to be the height of the shells. And then the width, or the thickness of the cross-section, we'll call that w. And then the distance to the middle of the rectangle, we're going to call that distance p. Okay. All right, and so if we set it up like that, and we imagine spinning it, this is what we get. Should have traced a line there, that was a mistake. So let's take this, remember this is our h, and then we're going to imagine spinning this around the axis. So let's see, that's 1, 2, 3. All right, and so if we do it, we'll get a shell. All right, something like this. Okay, so that's what we get. If we want to find the volume of that, we need to know the height. And there's a couple ways that we can go at this. The first way I'm going to show you is going to kind of piggyback off of the washer method, where what we'll do is we'll take the outside cylinder and subtract out the inside cylinder. All right, so if we were to do that, then the outside cylinder would have a radius of p, which goes to the center, plus half of w. This extra piece here would be half of w. So p plus w over 2. The inside radius would be p minus w over 2. Again, so p goes to the middle, subtract half of w, that gets you here. All right, and that information alone will get us the formula for volume of a shell. So for volume of a shell, it's going to be pi r squared h. R is going to be, for the big cylinder, is going to be p plus w over 2. So p plus w over 2 squared times h minus pi times p minus w over 2 squared times h. All right, so that's the volume of the shell if you take the large cylinder minus the small cylinder. Now you might think, wasn't this the washer method? No, it's not, because with the washer method we were shrinking the thickness of the washers, right, of this cylinder within a cylinder type thing. We were shrinking in this direction, right? And with shells, we're shrinking the thickness of the shell, as opposed to, but so essentially, instead of creating a washer here, we're going to create an infinitely thin shell of a cylinder, okay? All right, there's one other way that you can think about this, finding the volume, and I like it better. So basically, let me give you a reason give you my reason for liking it better. The volume of a shell, if you simplify this out, you expand everything and simplify it, you end up with this. Pi h times 2p w. Okay? And if you, so that's not obvious at first, but there's another way that you can think about finding the volume. In fact, let me give you the formula first, and then I will show you the other way to think about it. So here's the formula with actual functions now, okay? So let's do this. Let's sketch. Here's an axis. Here is a curve of some kind. We're going to go from C to D here. And then if you draw in some sort of cross section, or sorry, if you draw in a rectangle to give you this kind of a frame of reference, the distance to the rectangle is going to be P of y. And then the height of the rectangle, that's going to be H of y. And these two things are going to be in terms of y because the thickness of the shell, I should have written this bigger, I apologize, is going to be in terms of y. Or the thickness of the rectangle is in terms of y. Okay, so that means everything else is going to be in terms of y. So then our volume formula will end up being this. If we kind of move this around a little bit, we'll take the 2 pi out in front, the integral from C to D, and then P of y times H of y dy. All right, and so that formula, this is for a horizontal axis of revolution. Horizontal axis of revolution, all right? So to figure that out, or to kind of see why that might be, if you take and imagine this shell is infinitely thin, okay? So this is our shell, all right? And you were to cut it and you were to stretch it out like this, then what you would have, if we were to label the pieces, is this would be the height of the shell, h, right? And then the, so again, it was rolled up like this, so we unroll it. And then this length of the shell here, this distance here, would be the circumference of the circle. So, let's see, if we were to fold it up and then extend it, that would be the circumference, which is 2 pi r, but for some reason the book uses p for this distance, so it would be 2 pi times p. So the area of this would be 2 pi p times h times the thickness. If you look at our formula, we have 2 pi p times h. But the thickness is here, dy gets infinitely thin, okay? For a vertical axis of revolution then, this is what we get. So we have vertical axis of revolution. And then we have just some arbitrary region here. Okay, and remember that the rectangle is going to be parallel to the axis of revolution. So in this situation, we're going to be going around the vertical axis. And so in that case, our thickness will be in terms of x. The distance to the shell from the axis of revolution will be P of x. The height of the shells will be H of x. And then our formula then for volume will be 2 pi. And then we're going to go from A, which is here, to B, which is here. So it will be 2 pi, the integral from A to B, of P of x times H of x, whole with respect to x. Okay, so there's your formula for volume. So that's the first part. Let's put the examples in another video, so we kind of split this up into 2 parts here.